everybody. My name is Jim McMahon, and this is my SYST 584 research article review. Today we'll be talking about BayesChess, which is a computer engine that uses Bayesian networks to predict the next best move for the computer to make in a chess position. A little bit about myself. I'm working on my master's in data analytics engineering here at GMU, as I'm sure many of you are too. I do play chess. I'm not that great, but I do enjoy the game and studying the applications of these different engineering approaches to solving the different chess problems. In my day job, I work as a cost analyst for the U.S. Army. I support an IT program. The article I chose was titled BayesChess, a computer chess program based on Bayesian networks. I chose this because the approach to problem solving they use leverages a lot of techniques that we use in class. And I thought this would be a good case study to see, how this might be applied and maybe some broader implications of using Bayesian networks in a real-life situation. Some topics that we're going to cover today. We'll touch on the problem that these two gentlemen that built the system set out to solve. We'll also dive into a little bit more detail about the system, what they set out to do, some of the constraints, things that they didn't set out to solve, or problems that they didn't want to improve upon that were already kind of solved in the chess world already. We'll get into some of the details about how the system works, some of the algorithms that go into selecting the best possible move, defining the user's play style, figuring out a way to combine the information that they've gathered into a final answer to select a move. And then we'll get into some key takeaways about some of the strengths of the system that may apply in other situations, but also some of the weaknesses in their approach that maybe could be improved upon, or perhaps were just assumptions that they made in this particular case to support their project. Let's talk about some of the problems BayesChess sets out to solve, as well as some of the high-level characteristics of the BayesChess system. The main problem discussed in my research article is that modern chess engines can beat most human players of any skill level handily, with very rare exception. You're looking at one here on the left where Garry Kasparov beat the IBM computer Deep Blue, but even Kasparov lost the rematch the following year after Deep Blue had been improved. And we're talking about one of the best players in the history of chess. The big issue with this is that even top players think that the game played by these computer engines is generally pretty boring. They do the same thing every time. Their approach to the game is very similar no matter what moves are made by the user. And it just limits interest in playing with these products. People don't really want to pay for something that's going to kind of hammer them every time and not adjust based on the situation. And the solution suggested by the authors of my articles is maybe they could build something that adapts to the play style of the user. Modern engines do this a little bit, but what they want is for the algorithm to identify what type of play style the user has, where they're at in the game, and then change its approach to the game a little bit based on what the user is doing. So what is BayesChess? BayesChess is essentially the solution to that problem proposed by the two authors of my research paper who studied applied mathematics and statistics at the University of Almeria. Their program essentially uses Bayesian networks to create a more dynamic and interesting chess game that adapts to what the user is doing and changes a little bit every time. You're not going to see the same exact CPU strategy every game. This does lead to a little bit of a suboptimal chess engine, but it's more fun for the user to play against. What you're looking at here on the right is at the most fundamental level how they've kind of structured their Bayesian network, and several of structures that look like this are connected together to help the CPU decide what the best next move is at any given time. One of the most important things to note about this research article is that their system is constrained by several different things they set out to do, and it's important to keep these in mind as we kind of walk through how the system works. One of the most critical parts of their project is that they did not set out to be the optimal chess engine. They didn't want to be one of the best chess engines necessarily. They wanted to create something that was adaptive and that proved you could use this in other situations. So they're not going to be competitive with some of the big chess engines you might have heard of, like Deep Blue or Fritz or Stockfish. They're setting out to be a more adaptive, fun game to play and to create a proof of concept that shows you can use this for other situations where Bayesian networks make sense. They also assume that all chess moves can't be calculated. This pretty much holds true for all chess engines. There's so many possibilities at any given time that until you get to the very end of the game, there's really no way to calculate every possible thing that could happen in every possible tree of moves. So they assume that they're operating in an environment of incomplete information and that their probabilities help predict the best possible move in a given situation. They are still analyzing the position of the pieces to predict the best move, which means there is a combination of information here that's not just immediately built into the network. They use kind of a classic approach to analyzing the position of the pieces based on relative value of a piece on a given square, and we'll dive into that in a little bit more detail in a few minutes. Now that we've talked about some of the characteristics and constraints of the BayesChess system, let's talk about some of the lower level details about how this system works. The key first step for the CPU to make the optimal move is to analyze its position on the board. This is the non-Bayesian network piece of the puzzle, and this is something that all chess engines do regardless of how they decide to calculate the best possible move. In this particular case, BayesChess uses a min-max algorithm that gives a weighted score to the position of each piece on the board, and you can see an example of that here to the top right. We have a little grid that represents the chessboard under the hood of the BayesChess engine, and in this particular case we're looking at the scores given for the white knight. As you can see in the bottom row here, it gives the lowest possible score to a knight that hasn't moved from its starting position, indicating that the engine generally wants to apply regular chess principles that you want to get your pieces out and active on the board. But we also see that it doesn't like knights on the edge of the board, which is another generally accepted principle in chess. It favors pieces in the middle of the board, as shown by the highest score of 10 in the center of this grid. Each piece has a predefined value in the BayesChess engine. These are shown on the bottom right of this slide. These are pretty standard. As we can see, the bishop and knight have matching rankings. The pawn is the lowest, the queen is the most valuable. And we're really looking at a very small subset of the number of parameters captured here. As you can see, this would definitely be exponential. It would be captured for both the white and black pieces. And there's a number of pieces on the board that it has to track at any given time. The full algorithm is comprised of 838 parameters. And at the end of the day, it accounts for all of these using the Bayesian network to calculate the next best move. Some of these include the values of the pieces shown here, the different positions of the pieces, but a couple that we haven't talked about include, is the king in danger of being put in check, so it's checking to see if it's in danger of losing the game, or is a piece threatened, and it might rank those threatening pieces based on how valuable the piece in danger is. Now we're getting into one of the key parts of the solution proposed by the authors of my research article, which is defining the user's play style. This is one area of the BayesChess system where Bayesian networks are directly utilized. And basically the authors proposed that the user strategy be broken down into three possibilities, which are attacking style, positional play, or a mixed player, which indicates some mix of the two. The way they did this is they trained the system based on players that are considered top-tier players of all time for each type of play. They defined the attacking style as Bobby Fischer and Kasparov, positional play as Karpov, and a mixed play as Miguel Illescas, who is a Spanish grandmaster. They then trained the system based on thousands of games played by these grandmasters, and then the system will then change its style based on what it thinks the user is doing. If the opponent is an attacking style player, it attempts to minimize the probability of losing. If the opponent is positional, they attempt to maximize the probability of winning. And if it's mixed, the BayesChess system randomly selects its target goal. On the left-hand side of this slide, you can see the way BayesChess tries to quantify what the user is doing. Some of the key things that it's looking for is how many pieces are past a certain row on the board, has the user castled yet, what was their opening, Things like this help BayesChess define if the player is an attacking player, playing for position, or some combination of the two. Another area where Bayesian networks are directly utilized within the BayesChess engine is in the track game stage algorithm within the engine itself. Chess is generally accepted to be split into three main stages: the opening, which is roughly the first 10 moves, the mid-game, which is the section of the game immediately following the opening and prior to the endgame, and the endgame, which is typically defined as an area where most of the pieces have been removed from the board. BayesChess adapts its strategy to the stage of the game, creating a more dynamic and interesting game for the player. An example of this would be at the beginning of the game, the engine's going to protect its king and keep it safe from harm without moving it too much. But towards the end game, the engine might start moving its king out from safety in an attempt to assist its pawns moving up the board. This strategy is defined by making BayesChess play games against itself. We'll talk about these training games in a little bit more detail later, but the bottom line is the more games BayesChess can play against itself, the better BayesChess performs against opponents. A sample of the back-end database used by BayesChess to track how it's performing in certain situations is shown to the right. After accounting for things like the stage of the game, the player's strategy prediction, and the min-max position analysis, BayesChess takes all of these data points and combines them into a single Bayesian network. This network is then used to predict the next best move after a given amount of calculation time. This type of network is a really good fit for chess problems since chess problems are so probability heavy. We can't possibly calculate every possible outcome, but we can rule out bad moves, and we can see what the most likely possible answers would be, and potential alternatives as well. This approach also allows for situational computer strategy changes. For example, in the endgame, the king is a lot more active and is trying to help its pawns push up the board, but in the early game, moving your king out from safety would be unwise as it would lead to openings for the opponent to win. We've seen what BayesChess is doing under the hood. Now let's take a look at what it does well and what it does not do well. One of the things I found really interesting about the BayesChess engine is that they train the engine against itself. This is especially true for the situational analysis for the beginning, mid, and end games. BayesChess essentially plays a number of simulated games against the base BayesChess engine, and as the game plays against itself, it becomes more likely to win future games because it better understands what the best moves are at the beginning, mid, and end game. Looking at this chart here, you can see as the number of games on the x-axis increases, the engine is more likely to win future games. But interestingly, you can see on this red line here that between about 1100 and 1800 games, there's a point where the engine actually starts to lose a higher percentage of games as well. It's unclear from the article why this is, but my best suspicion is that the game may think that it knows more about what will create a winning situation and may go for the win more often now that it understands the game a little bit better. This indicates that maximizing the training game count is very important. The more games that we allow this engine to play, the better it will perform, especially towards the end game. The BayesChess system has many strengths, and I think that the authors and creators of this system accomplished a lot of what they set out to do. This is particularly true for the BayesChess engine serving as a proof of concept for Bayesian network use in situations where things are difficult to quantify. This was particularly true for the play style measurement. I would say play style is a difficult thing to quantify. It doesn't translate directly to an easy to define number like position analysis might, but I think they did a good job finding a way to translate this into something that a chess engine can understand and execute on. Another strength of this approach is that this data fusion strategy has non-chess applications. This shows that you can use these types of networks to try and capture things that are not necessarily written in stone in terms of numbers. A good example that jumps to mind based on some of my undergrad work would be creating some type of investment decision algorithm that accounts for user risk propensity. So is my user, risk averse, or are they reward seeking and willing to take on a little bit of extra risk in order to capture the potential for increased reward? I think that's another situation that could easily be modeled in a Bayesian network style. The other great thing about this BayesChess approach is that, in theory, this strategy is scalable. There's a lot of ways you can improve this engine without having to change too much about how it works. A couple of examples include they only used a couple different master players. They could add in some of the more modern masters that many people consider even more powerful at the game because they have the assistance of computers to learn. You could also build this into an already powerful chess engine and make it a little bit more robust and interesting to play against. You could add this to something like the Deep Blue we mentioned earlier, but have that engine change its strategy a little bit based on what the user is trying to do against it. The other thing that could definitely be done easily is incorporating more parameters to try and better define what the best moves are. A big piece of this would be increased computing power in the future, and I think that's another place where this BayesChess algorithm could definitely improve in the future. Well, I do think the creators of this system accomplished almost everything they set out to do. There are a number of notable weaknesses about the BayesChess system that should be discussed. From a chess perspective, right out of the gate, the min-max algorithm is a suboptimal chess engine, and it's not used by some of the best engines that are out there today. It was a really good fit for this particular drill because it matches well with the Bayesian network approach, and it made it easy for them to conduct their analysis. I also think that some of the piece values that were assigned native to the BayesChess engine would be debated by top players today. I think some type of dynamic value engine would have to be implemented here. Many people would argue that, for example, a knight is more valuable at the beginning of the game, where a lot of pieces are on the board and being able to hop over pieces is important, but towards the end game, bishops become more valuable because they can cover more open ground. This is something that could easily be built into the engine as is because they already have the BayesChess engine identifying what phase of the game that they're in. Maybe there's some type of multiplier they could incorporate depending on if they're at the beginning or the end game. I think another weakness of this approach was defining user strategy as three very distinct possibilities is a little bit limiting. They did this to likely save time and serve as a ground rule and assumption for their analysis, but I think that many players changed their strategy to fit the situation, and mapping these types of play to a couple different grandmasters seems a little bit short-sighted and isn't always necessarily true. Changing the end goal of the system based on the user strategy was not well explained in the article. It doesn't really make sense why the engine would be playing to minimize the chance of a loss if the opponent is attacking versus trying to maximize the chance of victory if the opponent is playing for position. It seems to me that that would be playing into the strategy of the players they measured against, since a player like Karpov, who they defined as playing for position, likely has a strategy for getting people to play into that position. But a player like Fischer wants people to play not to lose so he can try to exploit weaknesses more quickly. I think that this might be okay, but it needed some additional explanation. The other thing to note is that a lot of these things that I've identified as weaknesses are really just assumptions they made to support the analysis of their project, and they may very well have been aware of what they were doing and just accepted that as a potential weakness. A quick look at my work cited. I would highly encourage everybody to go check out this paper at the top citation there. It really was an interesting project with a lot of implications outside of the chess world, and it's particularly interesting to see how they conducted a couple of different experiments to see how the performance of the engine changed with number of simulated games incorporated into their model. Thank you all very much for your time. I really appreciate it. If you have any specific questions about the article or the work they did or anything that I showed in this presentation, feel free to shoot me an email at the address shown in this slide. But otherwise, have a great day.